Alright, let's explore the deep. Helicoprian teeth. In the coal-black seas of the early Permian period, roughly 290 million years ago, something hunted with a weapon that has no parallel in the history of vertebrate life. When Russian geologist Alexander Karpinsky first described the fossil in 1899, he held in his hands a perfect spiral of interlocking razor teeth, coiling inward like a circular saw blade, measuring up to 45 centimeters across. There was no jaw attached, no skull, no body, just the weapon and the silence around it. For over a century, that silence was the problem. Paleontologists proposed reconstruction after reconstruction, placing the whorl on the dorsal fin, on the snout, on the tip of the lower jaw, and each answer looked more impossible than the last. More than 150 specimens were recovered from sites across North America, Russia, and Australia, and nearly every single one yielded the same thing. The spiral, isolated, without the anatomy needed to explain it. No other known vertebrate in 500 million years of evolutionary history has ever produced a structure remotely like it. In 2013, Jesse Pruitt and Leif Tapanila at Idaho State University ran computed tomography scans through the best-preserved specimens and proposed a new answer. The whorl sat deep in the throat, behind the jaw, functioning like a conveyor belt of cutting edges. Helicoprion was likely not a true shark at all, but a ratfish, a chimera relative, wearing the most alien feeding apparatus ever evolved by a vertebrate animal. It was ancient enough to predate the dinosaurs and tough enough to survive the end Permian extinction, the single worst catastrophe in the history of life on Earth when over 90% of all marine species vanished. But the 2013 study did not close the case. It solved the location of the whorl. It did not solve the mechanics. Researchers still cannot demonstrate with confidence whether Helicoprion used that spiral to slice, to crush, or to spear its prey. A structure this elaborate, this metabolically expensive, this singular in the history of life, and we cannot show what it actually did in the water. We found the weapon, we just cannot figure out what it was for. And that gap between the evidence we have and the explanation we need is exactly where this list begins. Kraken bones. In 2011, at the annual meeting of the Geological Society of America, paleontologist Mark McMenamin of Mount Holyoke College made an announcement that stopped the room. He proposed that the largest marine predator of the Triassic period had not died of natural causes. It had been hunted, killed, and arranged by something else. Something that left almost no trace of itself in the fossil record. The predator in question was Shawnosaurus popularis, an ichthyosaur up to 14 meters long, recovered from Berlin Ichthyosaur State Park in Nevada. These were apex animals, the dominant hunters of the Triassic Sea. Finding a graveyard of them was already extraordinary, but McMenamin noticed something wrong with the bones. They were disarticulated and repositioned in the patterns that did not match the random scatter of death and decay. Some appeared to carry sucker-shaped markings on their surfaces. He proposed a Triassic kraken, a giant cephalopod of extraordinary size, intelligent enough to ambush, kill, and arrange the remains of 14-meter prey. The mainstream paleontological community pushed back immediately, and with reason. Wave action, scavenger behavior, and current drift can all produce bone arrangements that superficially suggest intention. Cephalopods, built almost entirely of soft tissue, fossilize extraordinarily rarely. The absence of a predator in the fossil record is not evidence of a predator. McMenamin's hypothesis was a conference presentation, not a peer-reviewed paper, and that distinction matters scientifically. But the underlying point survives the skepticism. The ocean's soft-bodied animals are nearly invisible to paleontology. Modern giant squid reach 13 meters in length and were not photographed alive until 2004, despite centuries of sailor accounts. The colossal squid, larger still, has never been observed alive in its natural habitat. Whatever ruled the deep in the Triassic, if it was built of muscle and ink rather than bone, we would have almost no way of knowing it existed. The Triassic kraken may be speculation, but the silence it exploits is completely real. Lilstock size. In 2018, fossil hunter Paul de La Salle was walking the beach at Lilstock in Somerset, England, when he found a bone fragment that did not fit the catalogue of anything known. Researcher Dean Lomax joined the analysis. The fragment was a cerangular, a section of lower jaw measuring roughly 1 meter in length. When Lomax and de La Salle published their findings in PLOS One, they were careful with their language, measured and conservative. The size estimates they offered were minimums. That caution makes what they wrote more unsettling, not less. At the time of its discovery, the largest confirmed animal ever to have lived was the blue whale, reaching lengths of up to 30 meters. The Lilstock specimen, scaled proportionally against every known ichthyosaur body plan, suggested an animal that may have reached between 20 and 26 meters. Longer, at minimum, than the largest blue whale on record. The authors described this as a conservative lower bound. They were not sensationalizing. They were reporting what the geometry of a single bone implied. That bone came from the late Triassic, approximately 205 million years ago, from seas that were warmer, shallower, and more productive than much of the modern ocean. A second potentially related specimen was found at Oscliffe, also in the United Kingdom, suggesting these animals were not singular aberrations. They may have been a population. A recurring presence in Triassic European waters, moving at a scale we have no word for in the modern ocean. The blue whale is presented in every natural history museum on Earth as the largest animal that has ever lived. School children are told this is fact. The Lilstock specimen, quietly published in a peer-reviewed journal by two careful scientists, challenges that designation without being able to confirm it. The size claim rests on one bone. The problem is that one bone is all we have, and the mathematics of that bone point somewhere enormous. One bone, one question. How large does something have to grow before the ocean simply swallows all evidence that it ever existed? Plesiosaur neck. In 1821, Mary Anning and William Conybeare described a creature pulled from the cliffs of Lyme Regis in Dorset, England, and the scientific world struggled to categorize what they were looking at. The animal had 4 broad flippers, a compact body, and a neck so long it constituted more than half the creature's total length. Elasmosaurus platyurus, one of the most extreme species, carried 72 cervical vertebrae, more than any other vertebrate ever documented. The image that crystallized in the public imagination was immediate. A long-necked sea serpent, head arcing high above the water, elegant and ancient and dangerous. That image is almost certainly wrong. And 200 years of study have failed to replace it with anything agreed upon. Plesiosaurs appeared in the fossil record approximately 200 million years ago and persisted until the end Cretaceous extinction 66 million years ago. For most of that time, their extraordinary necks were assumed to serve the obvious purpose, reaching into schools of fish, striking from above, using length as a hunting advantage. But a 2023 study published in iScience by Trina Du and colleagues analyzed the biomechanics of plesiosaur neck vertebrae and found something that contradicted the classic posture entirely. The neck was flexible downward, toward the seafloor, but was likely stiff laterally and resistant to the kind of sweeping, elevated arc that every reconstruction had assumed. The evidence points toward bottom feeding, threading the neck beneath prey schools from below, not above. The counterintuitive detail here is not just anatomical. The plesiosaur neck, that silhouette more responsible than any other for the global legend of the sea serpent, from Loch Ness to the Norse Hafgufa, was never fully understood by the civilization that built a mythology around it. We drew the monster on maps. We named it in every language. We put it in every natural history museum on the planet. 200 years of study and we still cannot say with confidence what that neck was for. Which raises a quieter question: what else are we describing in detail without understanding it all? Tully monster identity. In 1958, amateur fossil collector Francis Tully was digging through the Coal Age shales of Mason Creek in Illinois when he found something that stopped him completely. The creature had a long, flexible body, a proboscis tipped with a tiny claw-like jaw, rigid stalks extending from each side carrying its eyes, and a tail fin that suggested active swimming. He brought it to the Field Museum in Chicago. The scientists there looked at it and, by multiple accounts, could not place it in any known category of animal. It was formally named Tulemonstrum gregarium in 1966. Tully's monster. The name was more accurate than intended. Before Tully's discovery, the Mason Creek site was already recognized as one of the world's most important fossil deposits, a Lagerstätte, a place of exceptional preservation where soft tissues, not just bones, survive in the rock. Thousands of species have been recovered there. The preservation quality meant that whatever Tulemonstrum was, science had excellent material to work with. That made the failure to classify it more striking, not less. In 2016, a team led by Victoria McCoy published an analysis of over 1,200 specimens in Nature and declared the verdict. Tulemonstrums was a vertebrate, specifically a jawless fish related to lampreys, based on evidence of a notochord and gill structures. The case seemed closed. 3 years later, a 2019 study in paleontology by Lauren Sallin and colleagues systematically challenged the vertebrate interpretation, arguing the anatomical evidence was insufficient and ambiguous. As of the most recent research, the classification remains genuinely open. Illinois designated Tula monstrum its official state fossil in 1989. It appears on merchandise, in museum displays, in school curricula. It is celebrated. It is also, technically, an organism that modern science cannot place on the tree of life with any confidence. Not every creature fits the categories we have built. Some of them existed briefly, strangely, and left behind a shape that refuses to belong anywhere we have drawn a line: ocean acoustics. In August of 1997, hydrophone arrays operated by the National Oceanic and Atmospheric Administration across the equatorial Pacific Ocean recorded a signal unlike anything in the catalog. It rose in frequency over roughly 1 minute, peaking at a volume detectable across 5,000 kilometers of open ocean. The acoustic profile matched the signature of a biological source. The analysts called it the bloop. Then they asked the obvious question: what living thing is large enough to produce a sound at that scale? At the time of the recording, the answer was nothing known to science. The blue whale, the loudest animal on Earth, produces calls that travel hundreds of kilometers. The bloop traveled 5,000. For 15 years, it sat in the files as an unresolved biological anomaly, accumulating internet mythology and genuine scientific attention in roughly equal measure. In 2012, NOAA revisited the recording with better analytical tools and reclassified it as a cryosysm, the sound of a large section of Antarctic ice fracturing and shifting. The biological explanation was withdrawn, the bloop was solved, but the bloop was not the only signal. A sound designated Julia, recorded in 1999, lasted 15 seconds and has been less conclusively explained. A repeating signal called the upsweep, first detected in 1991 and recorded seasonally ever since, has no confirmed source. NOAA scientists have acknowledged that its origin remains unidentified. Less than 20% of the ocean floor has been mapped to high resolution. We have more detailed maps of the surface of Mars than of our own ocean bottom. Whatever is generating sound in the deep water column from ecosystems we have never visually surveyed, we cannot rule out with confidence simply because we have not found it. We solved the bloop. But the ocean is still talking, and some of what it is saying, we still do not have a word for. Ichthyosaur extinction. 90 million years ago, the most durable marine reptile in Earth's history disappeared. Not during a mass extinction, not alongside the dinosaurs. Quietly, during a period of gradual ocean warming and ecological restructuring, the ichthyosaurs simply stopped appearing in the fossil record, and no single explanation has fully accounted for why. The duration of their success makes the disappearance harder to understand, not easier. Ichthyosaurs first appeared approximately 250 million years ago. They survived the end Permian extinction, the worst catastrophe in the history of life, when over 90% of marine species vanished. They survived the end Triassic extinction. They evolved body forms ranging from dolphin-sized pursuit hunters to the enormous Triassic giants suggested by the Lilstock specimen. For 160 million years, they were a fixture of the world ocean. And then they were gone 30 million years before the asteroid that killed everything else. A 2021 study published in Nature Communications by Benjamin Keir and colleagues examined the pattern of ichthyosaur diversity in the millions of years before their disappearance and found a double vulnerability that may explain the collapse. Ichthyosaur diversity had been declining for millions of years before the final extinction, and simultaneously, the group had stopped producing new body forms. They were not adapting. The Cenomanian-Turonian oceanic anoxic event, a period of intense ocean warming and oxygen depletion approximately 93 million years ago, restructured marine food webs across the planet. The prey communities ichthyosaurs depended on may have collapsed first, leaving the predators without a foundation. The finding from the 2021 study carries a specific kind of weight. The real extinction, the loss of evolutionary flexibility, happened slowly, invisibly, millions of years before the last individual died. The population collapse was the final chapter of a story that had already ended in the genome long before it ended in the sea. They survived the apocalypse 3 times. And then the slow changes finished what the catastrophes could not: megalodon extinction. 3.6 million years ago, the largest predatory shark in Earth's history disappeared from the fossil record. Autodus megalodon reached estimated lengths of between 15 and 18 meters, weighed up to 100 metric tons, and produced a bite force estimated between 108,000 and 182,000 newtons, the most powerful bite of any animal ever documented. Its teeth, some the size of a human hand, are still found on ocean floors worldwide, dredged from depths of 4,000 meters. They do not fossilize in the conventional sense. They are the original material scattered across the seafloor, waiting. The animal is gone. The teeth remain. What makes the extinction of Megalodon scientifically unresolved is not the fact of its disappearance, but the cause. The Pliocene epoch brought significant changes to ocean circulation when the Central American Seaway closed, separating the Atlantic from the Pacific and disrupting the warm water ecosystems that Megalodon's prey depended on. Cooling oceans reduced the abundance of the large marine mammals that form the core of its diet. That explanation is broadly accepted. What it does not fully account for is the timing. A 2022 study by Catalina Pimiento and colleagues found that Megalodon's extinction coincided closely with the emergence and rapid expansion of the modern great white shark, Carcharodon carcharias. The evidence suggests direct ecological competition between the two species, with the smaller, more adaptable great white outcompeting Megalodon for prey in a changing ocean. The extinction may have been a combination of climate disruption and competitive displacement, neither factor sufficient alone. The deep-sea teeth once generated a cottage industry of claims that Megalodon survived into recent history. Those claims collapsed under precise radiometric dating, which placed every recovered tooth firmly in the Pliocene. But the fact that scientists were seriously using tooth dating to argue for or against a living 18-meter shark says something honest about the limits of what we can confirm in a 400 million cubic kilometer ocean. We know when it vanished. We know what it was capable of. What we do not fully know is what combination of forces in this ocean was enough to make it disappear. Cambrian explosion origins. 541 million years ago, in the shallow seas of the early Cambrian period, something happened to life on Earth that has no parallel before or since. In less than 25 million years, a span of time that is geological in scale but almost instantaneous compared to the 3 billion years of life that preceded it, virtually every major animal body plan that has ever existed appeared in the fossil record. Eyes, legs, shells, predators, nervous systems, mouths. Before it, soft-bodied, mostly immobile organisms drifting through Ediacaran seas. After it, the architecture of almost every animal alive today, including every bone in the human body. Charles Darwin recognized the problem in 1859 and called it, in his own words, the most obvious and forcible of the many objections that could be urged against his theory of gradual evolution. He expected the fossil record to show a slow accumulation of complexity. Instead, it showed a burst. He attributed the gap to the incompleteness of the geological record and expressed confidence that the missing transitions would be found. They have not been, not in the form his theory requires. The Burgess Shale in British Columbia, discovered by Charles Doolittle Walcott in 1909, and the Qingjiang fauna in Yunnan, China, discovered in 1984, are the two sites that have most illuminated the explosion. Together, they preserve animals so structurally strange that paleontologists spent decades misidentifying their basic anatomy. Hallucigenia, a creature with spine-covered legs and tentacles, was reconstructed upside down for years. Its front end was not correctly identified until 2015. Anomalocaris was initially described as 3 separate animals before anyone realized the claws, the mouth, and the body belonged to the same organism. Andrew Parker's light switch theory, proposed in 2003, argues that the evolution of the eye triggered the explosion, creating for the first time a predator-prey arms race that drove the rapid development of shells, speed, and complexity. It is compelling, it is also contested. No single explanation has achieved consensus. Every bone in your body traces back to something that appeared in a shallow Cambrian sea in what feels, geologically, like an overnight miracle. We have never explained the miracle, we have only named it. The deep ocean biosphere. Not 300 million years ago, not in the Cretaceous. Right now, at this moment, in the water column below 200 meters, in an ocean that covers 71% of this planet, creatures that have never been seen, named, or described by science are alive. The Census of Marine Life estimates that approximately 91% of marine species remain undiscovered. The ocean contains the vast majority of Earth's habitable volume. Less than 20% of its floor has been mapped to high resolution. We have better cartographic detail of the surface of Mars than of the terrain beneath our own deepest water. The deepest point on Earth, Challenger Deep in the Mariana Trench, reaches 10,935 meters. Crewed vehicles have descended to that depth on 4 documented occasions: Jacques Piccard and Don Walsh in 1960, filmmaker James Cameron in 2012, explorer Victor Vescovo in 2019, and a subsequent expedition in 2022. 4 visits to the deepest place on the planet. The Hadal zones, ocean regions below 6,000 meters, support life through chemosynthesis, entirely independent of sunlight, a biological process that was not discovered until hydrothermal vents were found in 1977. Entire ecosystems powered by chemistry rather than light had existed for billions of years before any human being knew they were possible. The giant squid, Archaetuthis dux, reaches 13 meters in length. It appeared in sailor accounts for centuries before science accepted it as real. It was not photographed alive until 2004. The colossal squid, Meson Ichthyothis hamiltoni, is larger still. It carries eyes 27 centimeters in diameter, the largest of any living animal, eyes thought to have evolved specifically to detect the bioluminescent disturbance created by approaching sperm whales in complete darkness. We have inferred an arms race between 2 of the largest animals on Earth, playing out in absolute darkness at crushing pressure, and we have witnessed none of it directly. In 2023, a NOAA deep-sea expedition off the western United States documented new species in real time during live-stream dives, coral formations, and invertebrates never previously recorded, appearing on camera for the first time in human history. Every prehistoric mystery on this list describes something we lost. The deep ocean is something we have never found, and whatever is living down there, in the dark, below the pressure and the silence, has had 541 million years since the Cambrian explosion to become something we do not have a name for yet. 10 items. 10 gaps where the explanation should be. And running through all of them is the same current. The ocean has been here for over 3 billion years, and we have been watching it seriously and with instruments for less than 2 centuries. Helicoprian's spiral sat unexplained for over 100 years. The plesiosaur neck has been misrepresented for 200. The Cambrian explosion has resisted explanation since Darwin identified the problem. These are not failures of attention, they are failures of scale. The ocean is simply older, deeper, and stranger than the frameworks we bring to it. What these mysteries reveal is not that science is inadequate, but that the ocean is genuinely, structurally, almost incomprehensibly large. Every answer we find opens the floor beneath our feet a little further, and the deeper we look, the clearer it becomes that we are not studying a closed archive. We are studying something still in progress. Subscribe and keep looking down. The handprint on the cave wall said, "I was here." The ocean says something older. It says, "You have barely arrived."